The first clean signal from Proxima Centauri arrived on Webb's mirror as a whisper, and within minutes the room went quiet in the wrong way. The infrared spectrum was supposed to be a milestone. It became a warning. The star, the public has been told, is our nearest, most promising neighbor, lit up Webb's detectors with a level of ultraviolet and X-ray violence that has no equivalent. Around our own sun. Then came the second signal. The atmospheric residue around Proxima b was not the calm signature of a sheltered world. It was the signature of a world being scoured. Tonight, I want to walk you through what Webb actually saw and why it should bother you. Not because the astronomy is exotic, but because the astronomy is honest, and the public version has not been. Here's the reversal you need to sit with first. For almost a decade, Proxima b has been marketed as the closest thing humanity has to a backup Earth. That framing was printed, repeated, and softened until it became a comfortable belief. The James Webb Space Telescope was supposed to confirm the promise. Instead, its infrared eye measured the environment honestly, and the honest measurement rules out the version of habitability the public was sold. What Webb saw isn't a doorway, it's a warning label written in light. Let's begin with the version of this story you've already heard. In August 2016, the European Southern Observatory announced a rocky, roughly Earth-mass planet orbiting Proxima Centauri, sitting inside the habitable zone. That phrase did the heaviest lifting of the entire announcement, because in every headline that followed, habitable zone quietly became habitable. Habitable became Earth-like, and Earth-like became backup plan. Each translation stripped a qualifier, and each qualifier was doing enormous scientific work. The habitable zone is not a promise of life. It's not even a promise of an atmosphere. It's a purely orbital definition, the distance range where liquid water could theoretically exist on a rocky surface if that surface has an atmosphere, if that atmosphere has the right composition, if the star behaves gently, if the planet has a magnetic field, if the geological history cooperated. That's a lot of ifs, and Proxima b runs into trouble on almost everyone. Follow-up papers through 2016 and 2017 modeled the radiation environment and concluded the planet has almost certainly lost most or all of its primordial atmosphere. The academic record has been walking away from the optimistic framing for nearly a decade. The public record has not. To understand what Webb saw, you have to understand what Proxima Centauri actually is, a red dwarf, an M-class star. The public impression is that red dwarfs are gentler, calmer neighbors. That impression is scientifically backward. M dwarfs are violent. Their interiors are fully convective. The entire star churns like boiling water from core to surface, tangling and snapping magnetic field lines constantly, releasing explosive flares that dwarf anything our sun produces. In March 2016, astronomers watched Proxima Centauri release a flare that increased its brightness by a factor of 68 in ultraviolet light in seconds. In 2019, another flare was recorded more than 100 times more energetic than anything the sun has produced in the modern record. And not as a rare event, but as normal weather. A flare like the 2019 event would dump the energy of a Carrington class event onto Proxima b in minutes. The 1859 Carrington event knocked out telegraph lines across an Earth protected by a full magnetosphere and thick atmosphere. Proxima b sits 20 times closer to its star than Earth sits to the sun, with no confirmed magnetosphere, and these flares are simply its normal weather. This connects to a deeper structural problem. To sit in the habitable zone of a red dwarf, a planet must orbit very close. Close enough that gravitational tides lock it, with one face permanently facing the star and the other permanently facing away. Tidal locking almost certainly kills the dynamo effect that generates a global magnetic field, because the planet no longer rotates the way Earth does. Without that field, everything else falls apart, because the magnetic field isn't decoration, it's the shield. On Earth, the magnetosphere is invisible, deflecting the solar wind and funneling charged particles toward the poles instead of stripping our air. Take that shield away, and the atmosphere becomes cargo the star is free to steal. We've watched this happen next door. Mars had an atmosphere, liquid water, and a magnetic field. Roughly 4 billion years ago, its dynamo faltered, the field weakened, and the solar wind began peeling the Martian atmosphere off, molecule by molecule, a process NASA's MAVEN mission still measures today, under a star far calmer than Proxima Centauri. Modeling estimates the stellar wind flux hitting Proxima b at somewhere between 1,000 and 2,000 times what Earth receives from the sun. Under those conditions, an Earth-like atmosphere would not survive geological ages. It wouldn't survive a fraction of one. To be fair, this doesn't prove no atmosphere at all survives. Exotic scenarios could offer limited protection. But the surface life version of this story is far harder to defend than the public version admits, and Webb's early atmospheric survey of Proxima b and the TRAPPIST-1 worlds is consistent with a harsher interpretation. Now break another comfortable assumption. Even if Proxima b were a paradise, we couldn't get there. Proxima Centauri sits 4.24 light years away, roughly 40 trillion kilometers, or the Earth-Sun distance. Human object ever to leave the solar system moves at about 17 kilometers per second. At that speed, it would take roughly 75,000 years to reach Proxima, longer than the history of agriculture, longer than the existence of cities, longer than the written word, several times over. And Voyager isn't even aimed at Proxima. Nothing we've ever launched is. Theoretical designs do better on paper. The Breakthrough Starshot initiative proposes accelerating gram-scale sails to 20% of light speed using ground-based lasers, cutting the trip to about 20 years. But 20% of light speed is a physics regime, not a spacecraft speed, a single dust grain. At that velocity, there's no known way to decelerate at the far end, and nothing that small can carry a human life support or return capability. It's a photograph, not a mission. Chemical and ion propulsion can't do it. Fusion propulsion doesn't exist as a working engine. Antimatter propulsion could work on paper if we could manufacture and store antimatter at rates trillions of times beyond our current capability. A trip to Proxima isn't a longer trip to Mars. It's a categorically different problem, one our civilization has no working answer for. Now put a body on the surface just to feel it. Assume generously the planet has an atmosphere and a magnetic field. Because it's tidally locked, the star never rises or sets. Fixed permanently in the sky on the day side, absent entirely on the night side. On the narrow terminator strip between them, one side of your body stays warmer than the other permanently, and the temperature differential drives wind strong enough to tear conventional shelters apart. The habitable strip on a tidally locked world isn't a garden. It's a permanent hurricane belt bordered by 2 dead zones, with no season and no relief. Then, there's the radiation. ISS crews absorb roughly 150 to 200 millisieverts across a 6-month rotation, and NASA caps career astronaut exposure around 600 to 1,200 millisieverts. During a Proxima flare, unshielded surface exposure could exceed a full career limit in hours. And there's circadian collapse. Human biology is tuned to a 24-hour rhythm set by this planet's rotation. On Proxima b, there is no day and no night, only a fixed red disk or permanent darkness. Antarctic winter over crews and long-duration astronauts already show that broken rhythms degrade sleep, immunity, and cognition. Here, the rhythm isn't broken, it's absent entirely. Within weeks, sleep would collapse. Within months, cognition would follow. Habitability was always a planetary science word. It was never a biological one. Now, widen the frame beyond the body. A radio signal from Proxima b takes 4.24 years to reach Earth, and a reply takes another 4.24 years. A single exchange takes 8.5 years. On Mars, the delay peaks at 24 minutes, and NASA already builds heavy autonomy into its rovers because even that is too long for real-time control. On Proxima, the delay isn't inconvenient, it's generational. There's no resupply architecture either. The ISS is resupplied every 2 to 3 months, and that cadence has failed before from an orbit only 400 kilometers up. A Proxima mission would never be resupplied, not in years, not in decades. Apollo 13's rescue window was measured in hours, and it worked because the crew stayed inside the Earth-Moon system. A Proxima crew would have no rescue window, no emergency return, no supply drop, and no signal fast enough to matter. Isolation stops being a mission hazard. It becomes the entire mission environment. So the question stops being, when do we go, and becomes something no agency wants to say out loud. With current physics, biology, and engineering, we cannot go. Not now, not soon, possibly not ever, in a form resembling the crude exploration we've imagined since the 1960s. Which raises the question of why the public tone stays so soft when the physical evidence is this hard. It isn't a conspiracy, it's an incentive structure. Astrobiology funding is defended in budget documents by the language of habitability, and the word potentially appears in exoplanet press releases constantly. Technical papers describe Proxima b as a rocky planet exposed to intense stellar activity with unresolved questions about atmospheric retention. Press releases describing those same papers use the word Earth-like. That's not a translation, it's a rewrite, happening at exactly the point where the public forms its beliefs. Most people never read the paper, they read the headline. And every layer in that chain, press office, news outlet, social post, has its own incentive to sound optimistic because optimism drives attention, attention drives budgets, and budgets drive careers. The researchers themselves have been clear in their journals. The softening happens in the pipeline between the journal and the public, which raises a harder question. If the nearest promising planet is this compromised, what does that say about the others? Proxima isn't an outlier, it's representative. Roughly 3 out of every 4 stars in the Milky Way are M dwarfs. and for years that statistic fueled optimism about common, habitable worlds. Webb is quietly dismantling that argument. In 2023, JWST observations of TRAPPIST-1b found no evidence of a thick atmosphere. Follow-up observations of TRAPPIST-1c reached the same conclusion. GJ-486b produced water vapor signals that turned out ambiguous between a real atmosphere and stellar contamination. LHS-3844b showed a bare rock signature consistent with no atmosphere at all. Every high-profile M-dwarf rocky planet Webb has examined closely has come back with the same failure mode. The list of promising candidates isn't growing, it's shrinking. If M-dwarf worlds are systematically failing to hold atmospheres, and sun-like stars are comparatively rare, the density of viable planets in the galaxy may be far lower than a generation of science communication implied. The Fermi paradox may not require exotic filters or dark forests. It may just require the honest admission that habitability is harder than we let ourselves believe. Here's what Webb has shown, consolidated. Stellar violence around Proxima Centauri isn't a possibility. It's measured. Magnetic shielding on Proxima b isn't present in any evidence we have. Atmospheric persistence under that flux is unlikely on geological timescales. The distance is unbridgeable with current or near-future propulsion, and that propulsion isn't being funded at any serious level. The biological fit of a human body to that environment fails simultaneously across radiation, circadian, thermal, and atmospheric axes. The communication and resupply architecture required doesn't exist and isn't on any real roadmap. And the galactic pattern, as Webb keeps looking, stays consistent. This isn't one bad planet, it's a signal about an entire class of worlds we were counting on to be common. That light traveled 4.24 years across a vacuum most human minds can't picture and landed on a mirror the size of a small building. It told us the planet we were sold as our nearest hope isn't a hope, it's a warning. It told us the sky isn't the vast catalog of options we imagined. It's smaller than that, much smaller. Earth isn't one option among many. On current evidence, Earth is the option, not one of many doors, but the one you're standing behind right now. Every generation before us has quietly assumed that if this one closed, there'd be another. Webb just knocked that assumption out. I'm not going to offer a frontier or a backup here because there isn't one on any timescale that matters to the people alive today, or their children, or their children's children. What there is, instead, is in systems keeping this one habitable. The atmosphere we take for granted, the magnetosphere we don't think about, the climate we treat as inconvenience, the oceans we treat as infinite, become the most important engineering problem of the century. Not because they're noble, but because they're all we have. The stars aren't hostile, they're indifferent. The shelter we already have is the one we've been treating as disposable. We are not looking for a second home. We are standing on the only one. The light Webb collected was 4.24 years old by the time it reached us, and it wasn't an invitation. It was a message. There's no next. There's only here. Act like it.